to your presentation.
Thank you, Fabian, for the introduction. So, my name is Francesco. As you said, today I'm going to speak about the phase field model of brittle fracture in heterogeneous bars. This is a work I developed together with my two supervisors, Pietro Carrara and Lorenzis at ETH Zurich. So, how does it work? Sorry?
The bottom button.
The bottom. I want to start saying that all materials are heterogeneous, but in many engineering applications it is sufficient to consider some effective homogeneous properties. Let's say that you want to study the fracture in the humerus, then according to this approach, the first question that the engineer is going to ask is what are the elastic modulus E0 and the specific fracture energy W1, that should be really too much to do. That has to be considered as a unique quantity for the whole structure. Well, this approach is good when the scale of the problem is much larger than the scale at which the heterogeneity comes into the picture, and actually this is not the case for the humerus. This is an image from a CT scan by Professor Yosibash, which is here, by Tel Aviv University, which clearly shows that there is a strong heterogeneity in the density that will come together with a strong heterogeneity also in the elastic modulus E0 and in the specific fracture energy. Then the question is what happens in the context of the phase field model when we introduce this dependence on X for the elastic modulus and the specific fracture energy to the observed quantities. And in particular, we want to give answer in terms of the elastic limit stress, the peak stress, and the fracture toughness. And we want to do that in a one-dimensional setting, which is the simplest setting that can show the main features of these heterogeneous materials. So I would like to give answer to this question by means of the following agenda. So we'll start with a general introduction of what is phase field for heterogeneous material. Then I will show you what we learned for elastic limit stress, peak stress, and fracture toughness. Then I will try to extend the observation I will make. And finally, I will draw some conclusions. So as I said, we want to study a one-dimensional setting. So here you have a bar with a length 2L, which is clamped from the left, and it is pulled from the right by means of a prescribed displacement, capital UT. The reference system X is centered at the midpoint of the bar, and in this problem here we want to study the evolution of two quantities. The first one is the displacement, and the second one is alpha, the damage variable. The second one is constrained by means of two conditions. The first one being alpha defined between 0 and 1, where alpha equal to 0 represents a locally sound material, whereas alpha equal to 1 represents a fully broken material in a point. The second condition is the irreversibility condition, telling you that the damage cannot decrease during the evolution process. Well, in the phase field approach, we find these two quantities by minimizing a total energy functional that, according to the 81 model, which is the typical choice for modeling brittle materials behavior, takes the following fashion. So it is made up of an elastic energy, which contains this elastic modulus E0, plus a second term, the dissipation, which contains the specific fracture energy, W1, that multiplies a bracket term, where you find a local term, alpha, and an local term, which depends on the spatial derivative of alpha. So that in order to be dimensionally consistent, we have to introduce a length, lowercase l, that we call the internal length of the phase field model. In this context, in order to introduce heterogeneity, we just need to prescribe these two quantities, E0 and W1, as function of the spatial coordinate x. Well, if you write the first order stability for this functional, then you will find two important conditions. The first one being the famous equilibrium equation, telling you that the stress sigma is just a constant along the problem domain. And the second condition is the damage criterion, which tells you that a left-hand side, which depends on a local release of elastic energy, should remain lower than or equal to a right-hand side, which depends on this W1. Notice that here, differently from the classical homogeneous case, you also have this W1 prime, which is the spatial derivative of W1. In the classical homogeneous case, you don't have this term because W1 is just a constant, so this derivative disappears. So in a sense, you can see this formulation as a generalization of the classical theory. So for this part of the presentation, let me introduce a very simple case of heterogeneity that I will extend this procedure, where you have an E0, which is constant along the problem domain and equal to E0 bar, and a specific fracture energy W1, which is like a piecewise straight line function, which can be mathematically expressed as here, where you have two important parameters. So the first one is this W1 bar, which is the minimum at the midpoint of the bar, And the second one is this length, LW, which is nothing but the reciprocal of the slope of the straight line. The dimensionless version of this slope is this R, which is defined as the internal length of the phase field over LW. Well, for this dimensionless slope, the limit case R tending to 0 is retrieved in two situations. The first one is when we approach the sharp crack model, so when L tends to 0, and the second case is when LW tends to infinity. Well, you can understand that when LW tends to infinity, then the slope of this straight line will go to 0. So again, we will have E0 equal to E0 bar, and W1 will be equal to a constant W1 bar. So we obtain an homogeneous material. We set this homogeneous material as a reference homogeneous material, meaning that we are going to compare all the quantities for this heterogeneous material with this reference one. For this reference material, we have all the interesting quantities thanks to the analysis by Pham and others. And in particular, what they found is that the elastic limit stress is equal to the peak stress, meaning that there is no hardening, so the stress can only decrease with an increase of the damage. And the second thing is that the fracture toughness can be interpreted just a simple rescaling of this W1 parameter. These two features are going to be different for the heterogeneous material, as I'm going to show you. So this is what we learned for the elastic limit stress and the peak stress. Let's start with the elastic limit stress, which is the stress found at the point where the damage starts to increase, which can be mathematically expressed with these blue conditions here, that put into the damage criterion will give us this equation here, which essentially states that the elastic limit stress for the heterogeneous material is equal to the one for the reference homogeneous material. Well, in the classical theory, right after this point, delocalization is explained as a loss of stability of the homogeneous solution. Then the question is there an homogeneous solution also for this heterogeneous material? Well, the short answer is no. Why? Let's assume by contradiction that alpha is equal to a constant. Then, if you plug this information into the damage criterion, you will find this equation here, which tells you that the left-hand side, which is constant, should be equal to the right-hand side, which depends on x. So this is impossible, so you cannot have an homogeneous solution for this material when alpha is strictly greater than 0. So that's why we look for a localized solution as the one depicted here, where you have a support of a length 2 delta. We solved the problem just in alpha domain because of the symmetry of the problem. And in this alpha domain, in this alpha support minus delta 0, the damage criterion becomes this equation here that will come together with corresponding boundary conditions, which tells you that the damage and its derivative at the end of the support are equal to 0, and that the special derivative of the damage at the midpoint of the bar is also equal to 0. Well, this is a very complex boundary value problem, so in order to simplify the treatment here, we just perform a change of coordinate from x to x tilde, and we move from a boundary value problem to an initial value problem. What do I mean? I mean that this first line of boundary condition will become an initial condition line, and we start integrating from this point, x tilde equal to 0, this equation through a Runge-Kutta scheme. This is the equation written for x tilde greater than 0. Then this second line becomes a final event, so we stop this integration when alpha prime is equal to 0. The problem here is that delta is a priori unknown, so we have to devise an iterative scheme to find this delta, and it's the following. We input simply guess value for delta, then we stop when alpha prime is equal to 0. At that point, we will find delta output, and when delta input is equal to delta output in absolute value, when delta input minus delta output in absolute value is lower than or equal to a very low number, then we will stop our scheme. So with this scheme, you can solve the equation that I showed to you before, and this is the results plot in stress displacement diagram. Here you have the solution for a case of a heterogeneous material where R is equal to 0.5, and what you can see is that the peak stress is greater than the elastic limit stress, and that from E to P you have an hardening regime. If you perform this computation for different values of R, then you will find this curve here, which shows you that the peak stress is monotonically increasing together with this dimensionless slope R. For what concerns the fracture toughness, well, first of all, the fracture toughness is the dissipated energy at the failure pseudotime, which is the pseudotime at which the bar breaks, meaning that the stress is going to be equal to 0. If you plug this information into the damage criterion, then you will end up with an ordinary differential equation, which is of the second order. So you need two boundary conditions, which unfortunately depends on delta, which is a priori unknown. So that's why you need a third boundary condition telling you that the damage at 0 is equal to 1. Luckily, this is a boundary value problem that we can solve analytically. So here you have the solution in terms of delta, and this is the analytical solution plotted for alpha. What you see is that the damage profile shrinks when the dimensional slope R increases. And for the fracture toughness, we find that it increases monotonically with the dimensional slope, similarly to what we have seen for the peak stress. So what we have seen so far can be summarized with this free expression telling you that the elastic limit stress does not change with the dimensional slope, whereas the peak stress and the fracture toughness increase monotonically together with this dimensional slope. What we have seen so far is true for a linear profile and for a heterogeneity in the specific fracture energy only. But we can extend this to further profile, like the parabolic one, where you don't have a slope at the midpoint of the bar, but you have a curvature that here is denoted with R, or for an exponential profile where you have both a slope and a curvature. Here R represents just the slope. Then you can extend, of course, this also to different heterogeneity, like heterogeneity in the elastic modulus only, or heterogeneity in both the specific fracture energy and the elastic modulus. And you will retrieve again the same qualitative trend, except for the case of the heterogeneity in the only elastic modulus, where GC remains a constant with R, because there you don't introduce heterogeneity in the dissipative term. So this makes sense. So finally, coming to conclusion, so what you have seen is that for an alpha strictly greater than 0, there is not an homogeneous solution, and the phase field shows a non-local effect that can be summarized with this free expression that I showed you before. So the elastic limit stress that did not change with the dimensionless slope, and the peak stress and the fracture toughness increase monotonically together with this dimensionless slope. That's all so far from my side, so thank you for your attention.
Yeah, thank you very much for the very interesting presentation. Are there questions? Yeah, maybe I have one question from the algorithmic point of view. Compared to classical phase field models, I mean, what exactly should be changed in order to take this effect into account then?
Actually, let's say the phase field model remains the same, just here we study what happens when you introduce something more with respect to a classical homogeneous material property. So essentially, if you want to go to practice in a finite element code, you just need to prescribe a GC and a E0, which are dependent on the Gauss point position. So, but the formulation remains the same, just the results then are different. And here we have some analytical results which can be good as a benchmark for, I don't know, studying bones, for example.
May I make a comment about that, because you don't really know what would be, for example, the L0 and what will be the numerical GC which you have to choose, because it depends on H over L. So this would also be something which, from the numerical point of view, have to be still investigated.
Yeah, here we are not using finite elements, so we don't have this issue. This is called semi-analytical, so this is a pure theory. But then when you pass to a finite element, of course, there is an error related to the size of the mesh you are using.
Because I guess you're going to compute also bones with a finite element code, right? So that means that you need to embed these approaches into the finite element model.
Yes.
Very interesting. Are there some more questions? Yeah?
So you change the fracture energy, the W, and kept the elastic modulus constant, but if still your application or your bones or something, always the Young's modulus is changing.
Yeah.
Did you perform the opposite analysis, change vary the Young's modulus and keep the fracture energy constant or vary both?
Yes. This is what you can see in this slide actually. In red you have the first case I show you just to show you the concept, and the results are in red here. Whereas in black here you have the results for the heterogeneity in the only elastic modulus, and you see that W1 is a constant. And then you have both heterogeneities in both the two properties, and you can see the result in blue. Of course, this is a simple case, but it's just to show the main features of when you have heterogeneity in both. You see that the trend qualitatively remains the same, you have this monotonical increase with R. Thank you for the question.
May I ask another one?
Yeah.
You consider to change E and W so that they don't have the same minimum at the same location?
Well, yes, I studied, I'll say here we want to highlight the main feature. Then in that case, we have to consider how they play together, and the minimum will move, or whether E0 as a minimum or where W1. So I thought it was less interesting, but of course this is important when you have a real problem to consider both. And also this was oriented to bones where the density probably is ruling both, and so I expect that where I have a minimum for one quantity, there I will also have the minimum for the same quantity. Yeah.
Okay, so thanks again.
Thank you.